name's Michael Roach. I'm a long-term earth science educator at the University of Tasmania, and I'm really a teaching intensive academic. So, what I'm going to show you stems from my desire to better educate our undergraduate students, but I hope that what I can show you a little later will also show how we can apply these same techniques for research and also for public outreach. And a few of the sort of virtual objects that we're going to talk about are displayed on the screen here at the moment. So where am I going to go? I'll talk a bit about the motivation and the issues behind what we're doing and why we're doing. Then I'll talk about a bit of technology. Let's try and work out where the button is. Oh, there it is. I'm going to talk a bit, it's a very strange button. I'm going to talk a little bit about how we do things, different types of visualizations, some software we produced, and show you how we integrate all that into virtual tours and their applications in geoscience education and research. And at the end, I've put in a few slides for some work I've recently done using the same techniques but in capturing cultural heritage. So hopefully that may be of interest to some people here. So first of all, why did I get involved in this? Well, as anyone who is an earth scientist or knows a little bit about earth sciences would know that fieldwork is an absolute cornerstone of geoscience education. But there are a whole heap of issues that are accompanying that, particularly in, say, in a university environment now. To take our students to show them things, it's not possible to take our students in Hobart to show them directly things in the Pilbara or in the Kimberley. And there's issues of time, cost, and very importantly now, issues of OH&S. There are places we used to take students 20 years ago, we just can't take them anymore on highways, etc. So I wanted to find ways where we could get around that. And conventional photography just really isn't adequate. And I'm going to tell you why it really isn't adequate. And there's a number of reasons for that. So the first of these reasons is about three-dimensional information. Geology is really three-dimensional. It's all about understanding three-dimensionality of things. Yet if I give you an individual one of those photographs, or even if I give you several of those photographs, it's a very difficult cognitive task to be able to take those photographs and, in your mind, turn them into a three-dimensional object. So we need to be able to depict, if we're going to do this properly, we need to be able to depict the geometry as well as just the texture. And there's a couple of different ways we can do that. One way is by laser scanning, and many of you may have been involved with things called terrestrial laser scanners that can collect incredibly dense point clouds of the surface of a building or a geological outcrop. I'm not going to talk about that. That's a high-tech solution and one which is not really appropriate to our needs. What I'm going to talk about is a technique called photogrammetry. And many of you may be aware of photogrammetry as it used to be applied. So in the past, we did photogrammetry from aerial photography. And if you went to the Lands Department in Hobart 20 years ago, they had big machines with prisms and wheels and lenses, and people would be staring down binocular microscopes and tracing contours onto maps. That's photogrammetry, but I'm going to talk to you about the way it's done in a modern sense. So let's talk a little bit about digital photogrammetry and how it works, because it's critical to understanding how it produced these sort of pictures. It all starts with taking images. And in the past, if you did photogrammetry in the past, you had to have cameras that were appropriately calibrated, have particular specifications so that all the characteristics were known. But that really changed initially with an initial publication in 1999, and then later in 2004, a main publication about something called the SIFT algorithm. SIFT stands for Scale Invariant Feature Transform. And what it means is that if you take photographs in two different locations at two different scales, this algorithm is able to pick common points between those photographs. And it underlies all the sorts of things that are coming in modern technology now, like driverless cars use this algorithm for being able to, in real time, detect things three-dimensionally in the landscape. So this was published in 2004, and it's led to a revolution in the way we do things. So we take a series of photographs, and as I'll explain in a minute, it doesn't have to be a particular type of camera. Now, once we get these photographs, we have to then work out the geometry of features. And just to give you an indication, if I have a camera and I hold it up here, take a photograph of you, there are 14 unknowns for every time I take a photograph. There are 6 unknowns that say where it is in space. 3 unknowns for where it is in space, 3 unknowns for what orientation the camera is, and 8 unknowns that say what's the characteristic of the lens. If I take 100 photographs, then we have 1,400 unknowns. So you might think this is a really hard mathematical problem. But the SIFT algorithm can find tens or hundreds of thousands of common points. And by doing that with a lot of mathematics, we can then work out where all the cameras are in space, and from that reconstruct the geometry. So we then infill the geometry to make something called a point cloud that I'll show you in a minute. And in a conventional sense from photogrammetry, if we'd been doing it for a map, we might then produce a digital elevation model or reproject it to make an ortho image, which some of you may have seen. However, today what we might do is make a fully triangulated three-dimensional model, and then we put texture onto that model, and it looks for all the world like a real object, and that's what I'm going to show you. So just a few things about image acquisition. You don't need a special camera. A phone will do, but if you're a good photographer, it makes a difference. So you can use any standard uncalibrated camera. You don't need to know the locations where you take the photos. That all gets resolved in the processing. And merely you just take photographs in many different orientations, and we can then synthesize those into a three-dimensional view. So this video, which we'll play now, will show this process. So this is an outcrop at Piccaninny Point on the east coast of Tasmania. The little blue things are the calculated positions of the cameras with little vectors showing where the camera's pointed. And those points in the background are the SIFT algorithm points. They're the points that the SIFT algorithm found. Then we infill those points. If you zoom in here far enough, we'll see that that's actually 2 million points, defining the geometry of that particular outcrop. And then if we zoom out a little, what will happen is in a moment, those 2 million points will be made into a series of triangles. And those triangles now will represent the geometry of the surface. It's a bit blurry on the screen, but I hope you can sort of see the triangles. So at that stage, what we've done is captured the geometry of the outcrop, which is further illustrated in this shaded relief model that you can see here. So by taking, in this case, 40 photographs and by half an hour's computer processing, we now have a geometrically correct representation. The next stage is then to put the texture map over the top, and what we have now is, if you like, a fully texture rendered representation that's true to scale of this particular geological outcrop. I started doing this about 2010, and I realised the immense advantages that we could have to be able to take something like this out of the field and bring it back into the classroom. And that's really what's motivated me to do this. But I'll show you research applications later on. We can do this also for samples. So we have it set up at UTAS where we spin samples on a turntable, we photograph them from many different locations, and then we can build fully texture rendered renditions of those samples. We've digitised most of all of our teaching collection, I would say now, and a lot of our research collection, so we can now bring up in digital form any of the rocks out of our rock catalogue that are important to us. These are just some examples from our first year teaching collection. So I hope you can see those samples are quite small. This is even smaller. Those crystals are about 5 millimetres across. So these are crystals of wolfenite. This is a single crystal of apatite, for instance, which we've been able to render fully in 3 dimensions. So these are just little videos. And of course we can now take samples like this, which we couldn't put in our teaching laboratories because A, the students would steal them, B, the students would scratch the shit out of them because they would want to test how hard they were, things like that. So we can now get things out of our archival collections, like this beautiful reptile skull from the Triassic near Hobart. We can get these things out of our archival collections and produce images or produce models which are showing the features we want the students to see. Just to give you an idea, for those of you who've seen some of the Permian rocks in Tasmania, a common fossil are bryozoan fossils like this, phenolstellid bryozoans. Those little apertures there are only 1 millimetre or 2 across. We've captured the geometry of those and their texture effectively enough to be able to do virtually all the taxonomic work we might want to actually do with those particular samples. Okay, the next question that really affects us when we're trying to capture the external environment from a geological and from many other perspectives is that we want to see it at multiple scales. As an earth scientist, I look at the landscape and I see the entirety of the landscape, but I also want to come down and look with my hand lens and see the small things. Single photographs just don't cut it. So we can't take a single photograph and then zoom in far enough to see the small things while also seeing the big things. But there are some technologies that enable us to do this. One of these is called Gigapixel Imagery. Take a camera with a big lens, put it on a robotic camera head, tell it you want to tile up 500 images, and it'll go ahead and collect 500 images. We can splice them together and make images that have billions of pixels instead of millions of pixels. And we can also do the same thing from photogrammetry using what's called ortho projection. But I'll show you examples of both of these. So first of all, let's have a look at a gigapixel image. It's not a Tasmanian one, but I think it's a pretty good one. So here you can see, I might have to start with the Chilean flag there. So we're near the border with Chile and Argentina. You can see that I can resolve the star on the Chilean flag here, but I can also see 1,500 metres of vertical relief in the rocks just here. And I can zoom in and see everything at that scale, to the scale of recognising something as small as a little star on a flag, right through to being able to see the entirety of the mountain range. So I think it's pretty good to be able to have a single image that enables us to capture all of that scale information. Then the third of the things that really affects our ability to be able to represent geological and, as you'll see later on, cultural heritage features is the issue of viewpoints. If we're just stuck to the ground, this is what we see. This is again Piccaninny Point, a place where we take our second year students. And if you're stuck to the ground, this is what you see of the geology. But if you can have a different perspective, then maybe you can get a lot more information. And of course, that different perspective most commonly is from above. And of course, coincident with this burgeoning field of photogrammetry came the availability of drones. So we can now take drones, we can fly them around, we can make photogrammetric models of features at a variety of different scales. We can get 2D images, as you've seen. We get high HD video, we can make 3D models, we can make 360-degree images, we can make a wide range of visualizations that enable us to be able to well depict the natural landscape. Here will be an example of this process. Again, this is Piccaninny Point. I've chosen the same thing. We've flown the whole of the outcrop. We take our second years at Piccaninny Point. The blue things are where the photographs were taken. So we've flown it at about 10 metres above the ground. The outcrop here would be about 60 or 70 metres across. And this is the photogrammetric model. The blue things will turn off in a second. And so what we can see is, apart from the computer glitching, what we can see is the entire outcrop. We can zoom in to anywhere on that outcrop. This is geometrically correct. It is located in three-dimensional space correctly, down to within a few centimetres at least. And so we can see all the features of this outcrop. And from this, we can also produce something called an ortho image. We can make a really high resolution image of the entire outcrop. And in this particular case, this ortho image has a resolution of about 2 millimetres. So we can see the whole 70 metre or 80 metre high rock outcrop, but we can see it with a resolution of 2 millimetres. So we can come in here and we can see not quite individual grains of sand. We can certainly in some places see individual minerals in the granitic rocks. So it's a pretty powerful thing that we can do with these sort of technologies. Another thing that we've done quite recently, and I'll show you some examples of this in a moment, is we said, well, drones are fine. Drones work if you're dealing with something 200 metres across, but if you've got to do something in the far southwest of the state, you've got to walk three days to get there, and you've only got a limited supply of batteries, etc. So we've applied this and then said, well, why don't we put it in a helicopter? So we've taken a standard helicopter, we've put a couple of high-resolution cameras in the helicopter. Here's a picture of it. We've got two roughly 50 megapixel cameras that are set on stabilisers, and they take photographs at 1 second intervals. We can fly around the Tasmanian landscape and digitise many of the iconic features that we see. Now I'll show you one example of this. This is Federation Peak in the southwest of Tasmania. So this is a fully texture-rendered three-dimensional model of Federation Peak. And I'll show you later on some more pictures from the ARTHs where we've analysed them. But you can see the amazing fidelity that we've been able to register something like this. It's an iconic piece of Tasmania's geological and geographical and iconographic, I suppose. It's an iconographic feature of Tasmania since it appears in so many features. We were able to digitise that. How long did it take us to do that? Well, it was 650 images, 2 cameras. It was about 5 minutes. We circled the peak for about 5 minutes in a helicopter, and we made an image that covers 1.6 kilometres across, 700 metres of vertical relief in this particular image. Another way that we would like to be able to see, if we take a photo, I'm in the field and I take a photo in that direction, what I lack is the context over there. So 360-degree images are another way to do this. And if you look at a 360-degree image without looking at it in the appropriate software, what you see is a big flat thing like this, but what you have to understand is that, oops, just gone forward, that wasn't what I meant to do. What you have to understand is that this edge is exactly the same point as that edge because it wraps 360 degrees around, and all the pixels on the top here are the points straight up, and all the pixels on the bottom is the point straight down. But if we put it in a viewing software, then we're able to see this from as though we were there. And later on, for those that wish to afterwards, I brought a VR headset. And I can get you here and put you in the VR headset, and you can be in a variety of different environments and looking around as though you're in those environments. So how do we do this? We can do this with a DSLR camera, take 6 images, splice them together, get about 140 megapixel image. In the last couple of years, you've been able to buy off the shelf a 360-degree camera, single press, you get 134 megapixel image of the whole 360 view. And we can also do this from a drone. Take it, fly 30-ish images in the air, splice it together, you get a 360-degree view. Just to illustrate that, here is an example of a 360-degree view not far from here. This is the coastline of Bellingham on the north coast of Tasmania, northeast from here. It's a fairly cloudy, rainy day when I did it, hence the fairly soupy colours. But this gives you the impression of what we can do. In the viewing software, this is now 50 metres above ground level, but this is a high-resolution image. We can zoom right in on it. It's 250 million pixels, so we can see all the details in these rocks. This is a place where we take our students to look at the geology, but we can also bring it to them in the classroom. They can look at it before they go into the field. They can look at it after they go into the field so that they can familiarise themselves with beforehand, but also go back and look at their interpretations in the context of these sort of data. Now, where all these resources reside? Over the course of the last 7 or 8 years, I produced a resource which is called AusGeol.org. So if you go to www.ausgeol.org, you will be able to download and interact with many of these models. This is actually the world's largest repository of digital geological models. We also have thousands of models we have up on something called Sketchfab, and I'm going to talk to you a little bit about some software we've developed as well. So let's go on and look at one of those. So this is the AusGeol database as you would see it on the web. I'll start going. I'm playing this at about 2 to 3 times real speed, so you'll see me typing faster than I normally do, etc. I'm here now, I've gone in here, I said I want to look at all the things that are folds at Malakuta in Victoria. I can click on one of these. Here's all the attribute information, the information about it. Click there, and we get the 360-degree view coming up in real time. This is available to you now. AusGeol.org will enable you to look at about 3,000 individual sites around Australia that document the geology. Here's an example of the interface. We can now go and say, let's look for faults. And so we'll go up into the New England fold belt and look at a reverse fault at a place called Bungwall. I have to assure you too that it's clearer than this when you're on a real screen. It's a bit blurry on the screen. Let's go to an iconic location some of you may have been to, but a very iconic Australian location for geologists, which is called Marble Bar. We're looking at rocks that are 3.5 to 3.6 billion years ago. Here's the overall view of it, done with the drone. Again, when you look at it on a real screen, it's less blurry. There's a little white hilux there. Some of you may be able to see to give you some context of scale. But then, in addition to looking at the overall outcrop, we can look at an individual outcrop like this. Now we're looking at something at the scale of 1 metre or 2. Another example of some complex geology at this location. All available to you on the AusGeol website. You can go to these locations, you can download the images, you can do whatever you like with them. And some more basalts at that location. And for that same light, here is an example of an ortho image from that 350 million pixel image, which gives you a resolution which is akin to what you might see with a hand lens at this particular location. And finally here, for those who may have been to Marble Bar, this is a rendition of what the Connegan River looks like at Marble Bar and the Marble Bar itself. And all of these are playing out of the AusGeol website, which is available to you anytime. So this is the AusGeol database. It's a database of visual representation of Australia's geology. In addition to that, we've got all of those models plus another couple of thousand models. I think it's close to 5,000 models now. In fact, it's well over 5,000. So we have about 5,000 three-dimensional geological models in our database within Sketchfab. Those models, and I'll play it now, those models, it's just flicking through here. If you go to www.sketchfab.com, AusGeol/models, you can look at large numbers. And they range from all sorts of scales and all sorts of types. Here is the Dolphin open pit on King Island in Bass Strait. So this is done with a drone. This is a wonderful outcrop on the outside of Maria Island, somewhere where most people don't get to go, but it shows what's called the pre-Permian unconformity. Here's another example of, at a scale of about 20 metres across, these are Triassic cliffs, but we can come to a different scale. This is at Marua in the west coast, little ripple marks fully displayed in 3 dimensions. Or we can look at a sample. Here's a sample from the Kilian gold mine in Indonesia, or a Triassic vertebrate fossil from Old Beach, all represented truly correctly geometrically with appropriate textures. You've already seen this other trilobite fossil again, it's just reappeared in this video. Some of these things are sorted into collections if you were to go online. I'll just show you one of the collections here in a moment. This is one we used for a third year prac, and this is an example of one of the samples out of our collection. So all of this is available free online. We adopt a policy that all of this should be free to everyone. We're not going to charge anyone to use any of this sort of stuff. Now, once I'd generated all these 3-dimensional objects, the question came about, how can we actually use them to do real work for our students? Because when we take students in the field, we don't just go and look and sort of maybe draw them in a book, but we do measurements. And so we developed some software that can replicate on these 3-dimensional models the range of different applications we do in the field. Now, some of this is a little bit more geologically technical, but I'll try and give you some impression of what's going on. So I'll just start playing it now. This is our software called GeoVis 3D. Here's an outcrop from South Australia. We might want to measure the orientation of some of those planes there. So now, and again running at about twice real speed, we can click on there and we can measure the orientation of the planes, which are plotted on a special diagram that we use up in the top right-hand corner. But we can also measure other things. So perhaps I want to measure, I hope you can see there's a bend in these rocks. That's called a fold, and that's something called the fold axis. So we're now tracing out the fold axis. These measurements are measurements that geological students would do when they're in the field. They would measure fold axes. They would measure the distribution of bedding planes in this particular environment. They could measure the orientation of lines in space, which is what's happening here. It doesn't matter about the details of what's happening in the top right-hand corner, but what you can see is we can take a geological outcrop and we can apply the same techniques we would do with a geological compass on the ground. We can apply that to interpreting a digital outcrop. And for me, this is really, really important. It's great to have a picture of the geology, but it's really important to be able to do something with it and to actually interpret it appropriately. And now another example, here's a 45-metre high cliff in New South Wales. We can come onto this cliff and measure. We couldn't go up there. It's crumbly as hell. I'd die if I tried to go up there. But we can now measure things accurately going up there and construct a geological log as quickly as you can see happening here. This is a true thickness geological log. We can also estimate grain sizes, etc. So this is a pretty powerful thing to be able to do both with our students and from a research perspective. If we acquire drone imagery of a large cliff, we can now go and measure the geology. Here's a finished interpretation of that outcrop, including the structural information, the thing up there in the top right, but also the measured vertical log there of 30-something metres of stratigraphy. Somewhere we couldn't measure. We could not physically go there to measure it, short of abseiling down from the top with a helmet on and getting rocks raining down on top of you. Okay, we use this software a lot in our undergraduate teaching, and this is just one example. Hugh on the right-hand side there did this interpretation of a rock. We had one really good rock we wanted to share with all our students. We had a class of 15 students. How can we share that one rock? We could pass it round. They could each get 10 seconds to look at it. But what we did was put the rock there, but we gave them the digital representation of the rock, and then they had to make their interpretation of what's called the paragenesis of the mineralogy in this rock. And this is Hugh's interpretation of the paragenesis of this rock, done in a fully digital situation. And when we did this, the students actually said to us, we preferred working with the digital version, because they could see the detail on that rock, on that digital rendition of the sample. They could see the detail for the entire rock, which was equivalent to what they could do with their hand lens. And so, although the rock was there, they said they actually preferred to work on the digital rendition of the rock to make their interpretation. Okay, so we've got a series. I've talked about then a series of different types of virtual resources. We've had fully texture rendered 3-dimensional models. We've talked about 360-degree images. We've talked about gigapixel images. How can we bring all that together? Well, we do so via things called virtual tours. So we've got the 3D models, we've got the 360-degree images, high-res imagery, a whole heap of other things, 360-degree video, normal video, plus other useful things like we can embed PDF copies of papers and things like that into it. And then we can produce a virtual tour, and I'd like to show you a couple of virtual tours that we've produced. So the first one is a mining-related one, and a lot of the things we do are related to mining. So here's from the Dolphin Mine on the west coast of Tasmania. So from this, the students can go and access, you've already seen this one, but can access the entire Dolphin open pit and look at it at a big scale, 300-400 metres across. This mine is going back into production as we speak. And all through the mine, we have 360-degree imagery. You can go and visit virtually any of the benches in this mine and look in detail at what you can see. And on particular benches, what we've acquired are other information, either detailed outcrop scale pictures, so this is some of the mineralisation at the Dolphin pit, detailed outcrop picture, but also what we've acquired are samples, and we then digitise those samples and combine them with laboratory information. So now in a moment, this is what the specimen might look like in natural light, but the mineral that we're looking for, or that they're looking for at Dolphin, is fluorescent in UV light. And so you can see here, the scheelite is the yellow stuff in this image. And we can combine that with laboratory analyses. We can get chemical analysis or microscopy images, and we can embed all of that into a seamless package that we can utilise for our students. And we utilise this very effectively, I think, within our master's programs and in part within our undergraduate programs. Here's another example. This one is a tour of Bluestone Bay. Many of you may have been to Freycinet Peninsula and gone out towards Cape Tourville Lighthouse and then walk down to Bluestone Bay. Bluestone Bay has some very, very special geological characteristics. I don't need to bother you with what they are right now, but we've built a virtual tour for there, and I'll show you one part of it if it plays. So here it goes. Yep. So we'll go down and have a look at that bit. This is an area we get our students to do some mapping on, and during COVID, we had a master's program. We had over 100 students from all around the world doing virtual mapping on this particular outcrop, which was pretty amazing. We had people in Peru, we had people in Africa, we had people in Europe simultaneously accessing our server and undertaking an interpretation project on this particular rock. So we can come down, this is now on a pole 6 metres above the ground. You can see the same outcrop, but we can come down to the outcrop and see what it looks like at outcrop scale. So now you're standing at normal human height. Or we could go and look at a three-dimensional model of that location just by clicking here. This is what it looks like within the virtual tour. Brings up the 3D model, and then you've got the 3D model which you can manipulate, look at, and potentially make measurements from as well. And so we utilise this sort of approach within our teaching program. It was an absolute saviour for us during COVID, as you can imagine. We were, of all the places in the world, we were probably the best equipped in the world to be able to translate into a fully digital environment during COVID, because we had a database of 3,000 or 4,000 virtual elements that we could integrate into our teaching. Now you might say, oh, this is crap, who wants to go and look at the rocks like this? Well sure, geologists would much rather be out there kicking it with their feet, smashing hammers, which you can't do in a national park, or looking at it with their hand lens. But we got really positive feedback from this. So here comes some feedback, hopefully, on click. I'll leave you to read the words, but we got really positive feedback about this. We had people who were entirely cynical about how effective it might be prior to doing it, who then came back and said, I didn't think it was going to work, but it worked really well. So we were really pleased and somewhat surprised that it did in fact work this well. So what I've really thus far shown you is applications for education. And as I said at the start, I'm primarily a teaching academic. My role has largely been in education rather than in research. But I also I'll show you a little bit more education, I'll show you some research applications. Just to show you that we're not limited to just looking at rocks in the field, I'll show you now some applications. This is a tour that I haven't quite finished, but we'll have a look at, oops, that didn't play. Why didn't that play? Go back. Clean. It should play. I'll go back 2 slides. I think I might have mucked up. Let's see if it plays on its own. No, it's not going to. Okay, you don't get to see the savagery of mine for some reason. It's not going to play.
No, it's playing.
Oh no, this is a different one. One other application that this has is for archiving geological features. Geology, you might think of, is absolutely static. Maybe everything's, the rocks are there, they're going to be there for thousands of years into the future, but elements of geology are actually really quite transient. And to illustrate that, new road cutting near Hobart on the left-hand side. You can see the amazing detail and the complexity in this. It's tertiary basalt on the left-hand side and tertiary mass flows deposits on the right-hand side. That was in 2019. Absolutely brilliant outcrop last week. That's what we see. So geology is transient, particularly in, say, a mining environment. They have a wonderful exposure, then they blow it all up and crush it up and send it out on a ship. And then they blow up a bit more of it. But by capturing it in this way, we preserve that geology in a way that can be utilised into the future. Here's now how we can use this in a more research environment. So this is now the outcrop on the outer side of Marar Island. And I hope that for those who aren't geoscientists, I hope that you might be able to see that the rocks up here are flat-lying and the ones down here aren't. And that boundary is called an unconformity. We can now, it's a spot we can't get to. We have to go out there in a boat, and if you want to actually go there and measure it, you have to jump off the boat in the surging waves and clamber up the cliff. We can do all our measurements. I won't bore you with the details of what these measurements show, but we can do all these measurements and fully annotate a geological model for this and do it in a fraction of the time that would be required for us to actually clamber on those rocks ourselves. So that's of all Tasmania's geology, that's one of the most spectacular sites. If you ever get the chance to go to the outer side of Marar Island, immediately below the Bishop and Clark, you will see the towering dolerite cliffs of the Bishop and Clark, but down near the water level you will see this contact between older folded rocks and younger flat-lying rocks. Here's another example from the Western Arthurs this time. And so it's Mount Hesperus on the Western Arthurs. We'll let it zoom up a little bit here. So that's 180 metres or something of cliff. And on that cliff you might just be able to see there's some wiggly lines. Those are folds. Now we could not go and measure there, or if I did I'd have to be roped up really severely. But I can now work out the form lines and then I can go and again do the measurements. Don't worry too much about what the measurements are showing in this particular case. But they enable us to work out the geometry of those folds in a remote sense. To acquire the data for this image would be less than 1 minute of helicopter time to do this. Yet we're able to go to a locality like this and acquire the information or some of the information we would have been able to acquire by visiting it on foot, but in many ways more information of a certain scale. Sure, we can't see it at the microscopic scale. I can't hit it with a hammer, I can't use my hand lens, but I can see the big things. And often it's the big things that are important. Just to finish then, I'd like to talk to you a little bit about how we can apply exactly these same techniques, but apply them to cultural heritage. And I've had the fortunate situation in the last month of being invited to do some archaeological work in Cape York. So a group from Griffiths and Flinders University are working in somewhere called the Laura Basin in Cape York, documenting Aboriginal rock art. This chap, Joseph, is one of the traditional owners. The traditional owners are keen to capture these artworks in a way that preserves them into the future, because obviously artworks are also transient at the scales of centuries. And one other factor, or one very important factor for them, was that many of these people cannot get out to these sites. This site was 4 hours walk from a road. We got in there in a 5-minute helicopter ride. It's 4 hours walk from the road. This traditional owner had never visited this art site because it was just too difficult to get there, and many of the old people couldn't get around. What they want to do is to produce virtual objects that enable them to show their own communities the artworks which are in inaccessible locations. So let's have a look at some here. This is one of the caves called Crocodile Cave, but strangely enough it doesn't have a crocodile in it, but we won't go into that. This is about 30 metres across. So now this is a fully texture rendered three-dimensional representation of that artwork cave, and I can, later on for those that are interested, I can put you in VR and you can walk through this cave and have a look at it. So, as you can see, it's a pretty important and well-decorated cave. Interestingly, just as a side story, what it does show, although I won't show it here now because the video is not going to focus on it, but over on the right-hand side they've depicted native troopers, because many of you may be aware that during the latter part of the 19th century, the regime in Queensland employed native troopers basically to fight other groups of Aboriginal people. And in this location, the Aboriginal people were basically fighting guns with sorcery. And there are paintings where they painted the native troopers horizontal because that was their way of trying to kill them with sorcery. And so this particular location depicts that really well, but I shan't, unfortunately. If you look in VR, I can show it to you later on. So we can also produce a virtual tour, and this is what I have in VR that you can actually go and have a look a little bit later on. I'll play this in a moment. This is the location. You can see it's quite rough topography, and we're right out in the middle of Cape York. We're going to go and visit that little dot with little man standing there, and unfortunately we're not hearing the background noise. I've collected ambient sound here as well, so we had the birds chirping and all that sort of stuff in the background. So let's move around. You can get an impression of the nature of the topography. It's reasonably rough. As I said, about a 4-hour walk from the road or 5 minutes in a helicopter. And now we'll go down into the cave. Here's the cave. You can just over there see the lying down figures, which were the native troopers. But now we can move around in that cave. And if you're in a virtual reality environment, which I can show you later on, then you would be standing there looking at these things as though you were in the cave. So I hope that you can see that the applications of what I'm showing you here extend beyond merely geoscience education, which is my primary interest, but they extend to geoscience research, and the same principles can be applied to cultural heritage practices. Not just at the Aboriginal cultural heritage, we could make a rendition of heritage buildings in Oatlands or something. We could have people walking through them in a virtual sense. Just a last example of the Archaeological Analysis. This is a flat platform. It's about 15 metres across, or a bit less than that, 8 metres across. And this is a platform that has a series of Aboriginal grind marks plus some petroglyphs on it. We acquired the photogrammetry of this. We also collected differential GPS, so we have a model that's both precise and accurate to within a centimetre and precise to a couple of millimetres. And so now if I play the model, here we go, if we look at this, you can see the grind marks there. But as we sweep to the right, you may or may not be able to pick out the shape of a human petroglyph there. Now, what we can do with our software, this is geophys software, is we can make the interpretation digital. Here's the interpretation of that outcrop, and as you'll see on the left, including some quite recent graffiti, which is where someone has created in 2007 has created their own petroglyph over the top of the Aboriginal ones, which is a rather sad situation. But this is the sort of thing which we can do. This extends beyond visualisation, this extends to analysis, if you like. So I'm trying to show you that it's not just pretty pictures, this is real interpretation of this. You know, these patterns that I've delineated in blue, red and yellow, we have them in full three-dimensional coordinates with accuracies of less than a centimetre and precision of a millimetre or something like that, which is a pretty amazing situation. The time to acquire that, about 2 minutes of photography, about 15 minutes of computer processing produced that particular rendition. So it's really quite time and cost effective. Okay, well I've hopefully not bored you, but I've shown you a little bit about what we do. I'd just like to summarise then. These things are really easy. I can go out with my mobile phone or any camera. I can collect multiple photographs in different orientations, build them into a three-dimensional object. In fact, today you can get apps for your phone that will do it. You can just point your phone, tell it to go, wave your phone around, and it'll build a three-dimensional object. It's that simple. 360 images, easy to acquire. You can just buy an off-the-shelf camera for a few $100 will acquire for you 360-degree imagery. So it's really easy. We've created at the University of Tasmania the world's largest resources of virtual geological information. As I said, we've got over 5,000 three-dimensional models on Sketchfab. We have the AusGeol database, which has 3,500 localities around Australia that we've documented. So we have this vast amount of geological information which is shared publicly. Everyone can access it. And during COVID, we had people from all over the world, geological departments, grabbing our data and using it for their undergraduate teaching because all of a sudden everyone couldn't be in the classroom and they had to have these sort of objects. We built software which we're fairly proud of because it works really, really well, and that software enables us to take it beyond just looking at stuff. It enables us to do the quantitative analyses of these outcrops or these cultural objects, as I indicated, that takes it beyond just mere visualizations. And what we do then is we take all these diverse visualisations together with other information like the laboratory analysis that I showed you before, or a seminal paper on a particular locality. We can embed these all into a virtual tour that's navigatable from any web browser. And I can show you some of those a little later in real time. And what I've tried to show down the bottom is, in addition to geology, it's no big step at all to go from a geological outcrop to a cave full of cave paintings, or to go from a geological outcrop to the facade of a Georgian building in Tasmania. Exactly the same process. It's entirely simple. A little bit harder if you want to do vegetation. Vegetation is really difficult to make 3D models of. It moves in the wind and it's diaphanous, the leaves are so thin. So it's really hard to make a 3D model of a tree, but things that are static and solid like buildings, caves, geology, it's easy. So what do I want to do in the future? Well, as was indicated, I'm about to retire as a teaching academic, but I want to continue in this process, and it's my little baby, if you like. And I'd like to continue in this process and continue to update the library, add lots of new geographic localities. One of the things that I think is really important, but which has not really been focused on, is that much of Australia's best geology doesn't exist out in the field. It exists in musty cupboards, in TMAG, in Geoscience Australia, at MRT, all over the place in repositories. The best paleontological samples, the best mineralogical samples are all in these repositories. No one ever sees them. You have to go and get special permissions to go in and fill out myriads of forms. Yet these are public institutions which, in my view, should have a desire to share these things. And the techniques that I've shown you, particularly with respect to geological samples, are very appropriate to that. I think we should be trying to unearth the treasures out of our vaults, really. I'd like to push that a bit more. I tried to push it with TMAG a few years ago, and pretty lukewarm, and how much is it going to cost us? I said, it's not going to cost you very much at all, just give us access to your vaults. Oh, too hard. So it was really quite hard. Maybe we're in the QV Museum here, maybe they are more amenable to accessing some of their collections. I'd like to increase the functionality of our software. It does good stuff, but we can make it do better. And we want to document mineral systems. I'm someone who works in the mineral systems area, so we want to document them from exploration to rehabilitation. And only last week I'm involved with a project with 3 European universities, and it's just been funded by the European Commission. We've got 400,000 euros over the next 2 years to build educational objects related to critical metals and critical minerals, which is obviously a very topical point in today's society. And we really want to then take it a bit further than that. Most of the things I've produced have been for undergraduate geology students or postgraduate geology students, and the tenor and nature of the information that we presented is not readily accessible to the public. But it's not a big step to go back to those virtual tours and change the language and make them more accessible to members of the general public. And I'm a one-man band, so what I need is multiple of me, more time and resources, but as was indicated, on the 29th of December this year, I ceased to be a university employee, and so I hope to be able to devote more of my time to this instead of other applications. So anyway, I hope that I haven't bored you. I hope that what you've seen has inspired you that we can go and do all sorts of things with our cultural and natural heritage in Tasmania and elsewhere, and that we can bring it in an engaging way to people, both in the classroom, but we can also build these sort of models and things that are useful for us from a research perspective and outreach perspective. So I might stop at that point. Very happy to answer questions, and I can bring up the AusGeol database on the screen and we can play with it, or we can, those that wish to hang around, we can put you in VR goggles and take you to a cave in Cape York if you wish to. So thank you for your attendance.